Okay, so in this video we're going to talk about mole-to-mole conversions. So before we've done a lot of conversions where we go from grams to moles and then we find molecules, or we go from molecules to moles and then we find some volume of space that they take up. Uh, so if we were to draw our kind of like mole island picture that we've used before, we would say that we've had moles, right, and we've gone to the volume island, right? And we used big M, which is molarity, that's moles over liters, right? We've also gone, and you can go back and forth, by the way. We've gone to mass island. You go to mass island using molar mass, which is measured in grams for every 1 mole. Or we've gone to particle island, which particles are either atoms or molecules in this case, and you use Avogadro's number 6.02 times 10 to the 23rd for every 1 mole. Okay? So our map has always looked like that, but now I'm going to add another component. That's going to say, actually, you can switch between mole of substance A and mole of substance B within a reaction as long as you have a balanced equation. And then from there, you can find mass of that, you can find volume of that, and you can find the particles of that. Okay? So that's where we're going today. For our first equation, we're going to say that 2a plus 3b goes to 5d and 4c. If you look here, the coefficients are from a balanced equation. They're representing the number of moles of that reactant needed or that product produced. So we'll go ahead and add that in. They represent moles. We get ratios from this. It's kind of like a recipe. So for instance, this one could be that 2 cups of sugar plus 3 sticks of butter make 4 batches of cookies, and I don't know what your other product could be, but we can make something up. Okay, so for our ratio of A to B, you get that directly from the equation. It is 2 to 3. We just took the numbers in front and used those. So that means if I plug in 2 moles of A into this equation, how much B would I have to react it with? I would have to react it with 3 moles of B, because that's what the equation says. And then, if I have 6 moles of B, how much C could I make? Well, what I would do, I'm actually going to take that and work that one up here. I'd start with 6 mole of B, put that over 1, and I would just multiply by our ratio. What's the ratio of C to B? Well, for every 3 moles of B that we use, we actually get 4 moles of C. So then we would multiply that out. 6 times 4 is 24, divided by 3 is 8. So you would get 8 mole of C. And that's your final answer. Awesome. Okay, so now we'll look at an actual equation. Your steps for these will be 1, to build it, and then 2nd, to balance it, and then finally identify the ratios that you need. Okay, so for this one, the equation is already built for you. It's a decomposition, and in this case, you're actually going to need to balance it to start. Okay, if we look, I'm not going to draw the table, but you'll notice that you have 3 oxygens on the left and 2 on the right. So we take those numbers, we switch them, and find a common multiple of 6. So I'm going to put a 2 in front on the left and a 3 in front on the right. That gives me 6 oxygens on either side. And then to match up our potassium and chlorine, I just need to place a 2 in front. So now the equation is balanced, yay. And then we can find the actual ratio that we need. Remember, this is like a recipe. So what's my ratio of KClO3 to O2? That is 2 to 3, just like in the last problem, actually. So if for your reaction you have 4 moles of KClO3, How much O2 can you produce? Well, you've doubled 2 to get to 4, so that means you would have to double 3 to figure out O2, so you would actually produce 6 moles of O2. Is it possible to find that using the ratio like math-wise like we did for the last one? Yes. You would just put 4 mole over 1, and that's of KClO3, and then you would multiply by our ratio, which is 2 KClO3 for every 3 O2, and those both are moles, but I just ran out of space and didn't write it. So KClO3 cancels, and that would give you 6 as well. In the next one, it asks, if you have 2.23 moles of KCl, how much KClO3 did you use? So now we're looking at, in red here, if you start with KCl, how much of KClO3 did you decompose? Well, if we look, our ratio is 2 to 2, which is the same as 1 to 1. So if I have 2.23 of KCl, that means I must have used 2.23 mole of KClO3 to get there. And that's our final answer. All right. So now it's a bit more complicated. Step 1 was to always build the equation if it's already in writing. Here it's already built for you. Step 2 is to balance. So let's go ahead and balance. If I look, I've got nitrate on either side. So I usually like to make the polyatomics match up. I'll put a 2 in front because you have 2 nitrates on the left and you need 2 on the right. Then that makes my Na different on the left and the right. So I'm going to go ahead and put a 2 in front, and that will actually balance it completely, and I'll just fill the rest in with 1s. All right, so now, otherwise, this problem is only different because it starts with grams. Okay, if we look back to our original map, this shows that you cannot go from moles of A to moles of B without using the ratio. And then if you have mass of one of those, like here, you must go to moles first, and then you can convert that to moles of the second substance. Okay, so that's going to be what we do right here. Okay, so first step, we're going to take 150 grams of NaCl. We'll put that over 1, and we'll convert to moles really quickly. Molar mass of NaCl is 58.5. That comes from the periodic table. Just add up the masses. It's really important in these problems to always write the molecule that you're working with every time. So if I do 150 divided by 58.5, that gives me 2.6 mole of NaCl. That's how much we're actually using. And then I can convert that to our product, PbCl2, very easily using my ratio. Okay, so step 1, convert. Step 2, we're going to find how many moles of product we would actually make. So I take my 2 moles of NaCl, and I'm going to multiply that by the ratio between NaCl and PbCl2. So that ratio is, according to our equation, so that recipe at the top, 2 mole of NaCl for every 1 mole of PbCl2. NaCl cancels, and then if we look, that means that I have 1.3 mole of PbCl2, and that is your final answer. All right. Now, it says, with that same reaction, let me go ahead and fill in how many grams of lead nitrate are necessary in order to fully react with that 150 grams of NaCl that we used earlier. Okay, I know, based on the last problem, that 150 grams of NaCl is actually 2.6 mole. So we're going to start from there. just to save ourselves some time. Okay, so I'm going to put 2.6 mole NaCl over 1, and I'm going to multiply. I'm going to multiply that into lead nitrate. I'm going to convert to lead nitrate in moles, and then convert moles of lead nitrate into grams, just to figure out how much of each we would need for our reaction. So in order to do that, I use my ratio. For every 2 moles of NaCl, I have to use 1 mole of lead nitrate, PbNO32. And when I do that math, I get my 1.3 mole of PbNO32. Then, as the next step, I can quickly convert to molar mass. So I'll take my lead nitrate, 1.3 moles, put that over 1, and multiply by the molar mass from the table of lead nitrate. And that's going to equal 430 grams of lead nitrate. Okay? And that is your final answer. So in order to fully react to that NaCl, you actually need a lot of lead nitrate. Okay, final one, and I'm going to move kind of quickly here. This is a combustion of ethane gas. Okay, so you're going to react 90 ethane with 75 grams of oxygen. This one requires us to balance the equation really quickly. So I'm going to do 1. I'll make my carbons match up really quick, 2 on each side. Make my hydrogens match up really quickly. And then I can leave this as a decimal for this problem because we're using the ratio. And it'll be a lot easier that way. Okay? So how much carbon dioxide can I make in moles? And then finally, how much can I make in grams? So I'm going to ignore this bit for now, but we know that we're going to be making carbon dioxide in grams. First, I'm going to take both my products and convert them to carbon dioxide. Whichever one gives me the least amount of carbon dioxide, that's actually the max that I can make. Even if I have extra, it doesn't matter. Okay? So what I'm going to start you with, let's convert ethane, 90 grams over 1 of C2H6. I'm going to convert that to moles. In order to do that, you're going to divide by 30 grams. That will give me moles of C2H6. And I'm going to show this one as 2 steps, okay? So all in one, here's the first step, and the next step will be here where you use the ratio. The ratio between this guy and CO2 is 2 mole of CO2 for every 1 mole of C2H6. So when you do all of that math, it should give you 6 mole of CO2. Okay, and your units will for sure cancel. Let's remember that work there. We'll go back and forth really quickly, and we'll again solve the grams problem in a second. So now let's convert 75 grams of oxygen to moles of CO2. So I'm going to divide by the molar mass of oxygen to get it into moles, which is what we have now done in this step. So that will be step 1. Step 2, it's going to happen over here. You're going to use the ratio. The ratio for O2 to CO2 is strange. It is 3.5 mole of O2 for every 1 mole of CO2, or for every 2 moles of CO2, excuse me. When you multiply that out, it gives you 1.34 mole of O2, or of CO2. Okay. From that point forward, we can multiply by 44 grams per 1 mole. That is the molar mass of CO2. That'll give you a final answer of 59 grams of CO2. The reason why, because 75 grams of oxygen will produce your 1.34 mole of CO2, excuse the handwriting, whereas the ethane will actually produce more. You have to go with the one that produces less, even if you have extra. Okay, So that's your final answer.